Good morning. In this video, we will discuss the chapter 3 top level view of computer function and interconnections. Let's look into the computer components. Actually, the latest computer designs are based on the concepts which were developed by the concepts were developed by John von Neumann, who is from the Institute of Advanced Studies, IAS, Princeton. Okay, fine. The three key concepts of John von Neumann architecture is, the first key concept is the data and programs, or data are instructions. They are saved in the computer memory. Okay, fine. Read-write memory, single read-write memory. So this is what it's called as a stored program concept, the first one. Okay. And the content of the memory are addressable by the locations, no matter of the type of data. It's about the idea. The contents of the memory are addressable by location. Okay. And the third key concept is execution occurs in sequential manner, like one after another. Unless otherwise, if the instruction is a jump instruction, it won't have the sequential execution. Fine. Now let's look into the terminology called hardwired program. Okay, fine. So actually, in case of hardwired program, let's assume a set of logic components, basic logic components. They are connected in a way to store some binary data and to perform some specific arithmetic and logical operations on that data. Okay, so it has some data and it will do some operation on that data. What operation? Some specific arithmetic and logical operations on that data. Okay, so particular computation is to be performed. Let's say if you want to have a specific computation to do to be performed, so you can program in a way to connect the components to perform that specific action. Okay, so the process of connecting various components in a desired way to do some kind of computation, it results in a program. Is it the outcome? Outcome is the set of components. That components will perform some specific action. So that's the resulting program. Program means don't think it's a program. Program, I'm talking about the set of components doing some specific action. That's the resulting program. Okay, so that resulting program, actually it's a hardware. Okay, fine. That is called hardwired program. Okay, then do not confuse with the terminology program. I'm not referring the program. The program here refers to the set of components, the logic components. They are connected in a way to perform some specific computation or some specific operation. Okay, that's the hardwired program. Okay, let's see some alternative. Alternative means another one. This is the previous one. Hardwired program is doing some specific computation. Okay, so the hardware, the set of components, the hardware are connected in a way to perform some specific action. Okay, a contrast to this is general purpose configuration of the logic components. What do you mean by general purpose? The components can perform any computations or any function, various function. So they can perform various functions. Okay, so that means the set of hardware will perform various functions on the data. Fine, but how? What function it's going to perform? I say various, is it? So that various function depends on the control signals applied to that hardware. So based on the control signal, it will do some specific action. Okay, fine. So in the previous example, the hardwired program, the set of components are configured in a way to perform some specific action or specific function. Here, the set of components will perform various function on the data based on the control signal. Okay, so this is the idea. Okay, so here I say that based on the control signal, the set of components will perform some action. Okay, here I am talking about set of components. Let's call it general purpose arithmetic and logical function. Okay, instead of calling as components, logic components, let's put a proper terminology, maybe arithmetic and logic functions. Okay, fine. So how the control signals are going to be supplied to the component? general purpose arithmetic and logic functions component. Okay, how are we going to supply the control signal? Fine. Actually, your program is a sequence of steps. Okay, every step will have some specific action. Okay, every step will have some sort of arithmetic different arithmetic and logical operations. Okay, it needs to do some different arithmetic and logical operations. Okay, fine. So for each step, a new set of control signal is needed. For addition, we need a different control signal. For loading instruction, we need different control signal. For store instruction, we need a different control signal. Okay, fine. So there will be a unique code for each possible set of control signals. Okay, so read control signal means the read instructions, and for arithmetic instruction, different control signals, something like that. Okay, let's provide unique code for each possible control signals. Okay, fine. And add to the general purpose hardware a segment called, here in the diagram you can see a segment called instruction interpreter. Can you see this one, instruction interpreter, this segment? So what it will do, this instruction interpreter will accept the code and generate the control signal based on the code. If the code is a load instruction, it generates load control signal. If the code is a store instruction, it generates the store control signal, whatever is it. So this instruction interpreter, this segment will accept the code and generate the control signal. So there are two components. There are two major components in the system. As you see that, one is the general purpose arithmetic and logical unit. Another one on the top, you see another segment called instruction interpreter. So together, these two together is called CPU, central processing unit. Okay, fine. So actually central processing unit has some other components also. Okay, fine. It's not the one and only two components of the central processing unit, but just have an idea. This is the segment. Instruction interpreter is the one generating the control signals, and that's sent to the arithmetic and logical unit, ALU. Fine. So here we need some input module. So the input module contains a basic components for accepting the data and instruction in some form. Okay, and then convert them into a form of control signals, so that the ALU can understand it. Okay, so a means of reporting the result is needed, and this is in the form of output module. Okay, fine. So together it's referred to as IO components. Okay, so it receives the data, it accepts the data and instructions, and then it processes the data and instruction and generates the control signals, and that's sent to the ALU. Okay, so who is doing all these things? Instruction interpreter. That segment is doing this. Actually, it's not the one and only components. We need some other components also. Okay, what are the other component we need? An input device. Okay, we need an input device that will bring the instructions and data in a sequential manner. Okay, then because you already know that instruction execution will go on in a sequential manner. This is what the architecture, the key concept of John von Neumann architecture says. Okay, fine. Instruction execution goes in a sequential manner. But in case sometimes the program may have some explicit jump instructions. Okay, in case of the jump instruction, execution won't be in sequential manner. Okay, so operations on the data may require access to more than one element at a time in a predetermined sequence. Okay, fine. We may need to access more than one element at a time. So we need to place the data and also the instructions temporarily. Okay, fine. The instructions need to be kept and also the data needs to be kept temporarily. So actually that is the main memory which is going to hold your data and instructions. Okay. This internal memory, or else you can say that main memory, it's different from the external memory. Okay, or the peripheral devices. Okay, fine. the primary memory. The main memory is way different from the external storage. Fine. John von Neumann pointed out that the same memory could be used for both instruction and data. So the main memory going to hold the instruction and also the data. Okay, you don't have to have a separate memory for a data and instruction. The same memory, it will have two segments. One segment will keep the instructions and another segment can keep the data. Okay. Actually, memory consists of set of locations. Each locations are numbered addresses. Okay, they are sequentially numbered addresses. So each location contains a binary number that can be interpreted as either instruction or data. So because I just now mentioned that memory going to have the data or instructions. Okay, fine. So each location contains something. It can be a data or instructions. So the I/O module transfers the data from the external device to the CPU and main memory and vice versa. So I/O module takes the data from the external device and then send it to the CPU and memory. Okay, store it in the memory. Okay, then this is what John von Neumann said. Program and data are stored in the memory. Fine. Let's look into the computer components, top level view of the computer components. In chapter 1, we saw that hierarchical system. The main components of the computer system is CPU, I/O, main memory, okay, and the interconnections between them, the system bus. So here you can see the three components, CPU, main memory and the I/O. In between you can see the interconnections between the component, system bus, bidirectional bus, okay. Here you may see some terminologies used here, especially in CPU. There are some terms used there. PCIR, MAR, MBR, IOAR, IOBR. What are they? They are the registers. Okay. PC means it's program counter. IR is the instruction register. MAR, memory address register. MBR, memory buffer register. IOAR, input output address register, and then the last one IOBR, input output buffer register. We are going to see some of these registers in the upcoming slides in detail. One other component CPU contain is the execution unit. That's the ALU, arithmetic and logical unit. So these are the registers that we saw in the previous slide. MAR, MBR, IOAR, IOBR. What are they? Actually, the basic function of a computer system is data processing, execution of the program. So actually the program consists of set of instructions. Where is the program? The program is stored in the memory. We saw it in the previous slides. So the processor does the actual work by executing the instructions. Where are the instructions? Instructions are in the memory. Okay, fine. The instructions are the program. Fine. The key elements of the program execution are described as a function of the registers. So these are the four registers. We need to know these four registers better. First one, memory address register. Memory address register. From the name you can understand that it specifies the address in memory for the next read or for the next write. For the next read and write. Fine. And then memory buffer register. Buffer contains the data to be returned to the memory or to be read which is received from the memory. Okay then. To be returned into the memory or received from the memory. Okay, fine. And then IOAR, address register. That is the address of the particular input-output device. IOBR, buffer register. Buffer registers contains the data to be sent to the output device or received from the input device. So, continuation of the previous slide, the main function of the computer system is data processing. Okay then. So, the processing happens in two steps. Okay. So, it consists of two steps. What are the two steps? Fetching, executing. That is the main two steps. Fetching the instruction, executing the instruction. So, let's see. The first step, processor fetches the instruction from memory one at a time, by the way. Okay, this is what John von Neumann said. Execution occurs in sequential manner. Okay, fine. So processor reads the instruction from memory one at a time. And then the second step is execute the instruction, each instruction. Okay, fine. So program execution is a repeating process. What does it mean, repeating process? Fetch, execute. Again, fetch the next instruction, execute. And then fetch the third instruction, execute. And then fetch the fourth instruction and execute. It's a repeating process until the end of the program. Okay, fine. The processing required for a single instruction is called instruction cycle. Okay, then. So, fetch and execute. That two steps is called instruction cycle. So, it has the two-step description. It's given in the diagram below. This instruction cycle. Instruction cycle means what? Processing required for single instruction. Okay, then. If two steps are referred as a fetch cycle and execute cycle, the program execution halts only if the machine is turned off, or else it will continue fetch, execute, fetch, execute, fetch, execute until the error occurs, maybe. Because after when an error occurs, it can't continue. Okay, then, or else the program instruction that halts the computer is encountered. Maybe there is an instruction in the program that makes the computer to hold for a second or some time. Okay, halt for a second. Okay, let's see the first step, instruction fetch. Because there are two steps, is it? Fetch, execute. Okay, then. So the first step is instruction fetch. At the beginning of each instruction cycle, the processor fetches the instruction from memory. Okay, then how it fetches the instruction from memory? Because memory is a addressable locations, collection of addressable locations. So from which location the processor is going to fetch the instruction? The second step. Can you see the program counter holds the address of the instruction to be fetched. So based on the content of the program counter, it has the address. The program counter has the address of the instruction to be fetched next. So based on that, the processor fetches the instruction from memory. After fetching the instruction, the processor increments the PC content. Okay, so let's assume the address is 100. It will increment to 101. What is 101? Address of the instruction. Next instruction, address of the following instruction. So processor increments the PC after each fetch instruction. Okay, fine. The fetched instruction. What happens to the fetched instruction? The processor keeps it in a register called IR, instruction register. So this is another register. IR is another register. It contains the fetched instruction. So the fetched instruction is kept in IR. PC contains the address of the instruction to be fetched next. So here in the slide, we are looking at two registers, PC, IR. Okay, then after the instruction is moved to IR, the processor interprets the instruction and then performs the required action. Interprets means decoding the instruction. So what is that instruction? What to do? What is the operation? So it understands and then it performs the required action. So this is about instruction fetch. The example is given, so you can go through the example for your better understanding, which is given in the paragraph. The next step is execute, instruction execute. Okay, so the fetched instruction is loaded into the register which is called IR. I already mentioned in the previous slide, is it? So the instruction contains zeros and ones. Okay, then. So that zeros and ones tells the processor what operation to be performed. So what the processor does? Processor interprets the instruction and it performs the required action. So that is about the instruction execute. Okay, fine. So that action falls into four categories. So what are the four categories? Processor to memory, processor, IO, data processing, control. Okay, this is the four actions. Actually, these four actions we already discussed in chapter 1. Four main functions of the computer system. So that is the same four main functions, but some functions name are reworded. Only that is the difference. Okay, fine. So the first action is processor memory. What does it mean? Data may be transferred from processor to memory or from memory to processor. So data is transferred between processor and memory. This is first action. Second action, processor IO. What does it mean? Data may be transferred from processor to the peripheral device, I mean to say output device, or from input device to the processor. Okay, fine. And the third action may be processing. That is, the processor performs the action, the operation. What operation? Arithmetic and logical operations on the data. Okay, fine. And the last action may be the instruction may specify a sequence of execution to be altered. Something like a jump instruction, where the next instruction to be executed will be somewhere, not the next instruction, somewhere else in the program. Can you get the idea? Branching. This is what you call branching. Okay, fine. So again, the example is given in the paragraph. I would like you to read it and understand it. Okay, let's assume the instruction execution by having some sort of instruction format, and we will see one simple example also. Let's assume this is the IAS instruction format. In the first diagram, it's given 0 to 15. That means, what does it mean? Every instruction takes 16 bits. What are they? 0 to 15 means 16 bits. So the first 4 bits, 0 to 3, are for the opcode, and the remaining 12 bits are for the address. Address means operand. Okay, the address of the operand. Okay, let's assume this is the instruction format. Okay, fine. And below that some description is given. Program counter, PC means address of the instruction to be executed next, and instruction register IR, that register keeps the instruction being executed. And then another register, this is a new register we didn't see in the previous slide, accumulator. Down below in the diagram, can you see here accumulator? Accumulator, AC means temporary storage. Sometimes you may need to have a temporary storage during the calculations. Maybe you need to hold the result for some time. Okay, so that's the use of accumulator. Okay, then down there got some other bits, and the explanation is given. Let's assume that the sequence of bits 0, 0, 0, 1, that means load instruction, load AC from memory. And then 0, 0, 1, 0 means store AC to memory. Okay, another one, 0, 1, 0, 1 means add the content of AC and then the memory content. Okay, this is the meaning of these bits. Actually, these are called opcodes. You know, in the previous above there in the instruction format, in diagram A, I told you first 4 bits tells you the opcode. So this is the 4 bits. If the 4 bits are 0001, it means it's a load instruction. If the 4 bit is 0010, it's a store instruction. If the 4 bit is 0101, it's an add instruction. Okay then. So let's assume this way. So now let's see one example. How a program will be executed in a sequential manner. So here is the example for the instruction execution. Okay then. So let's assume in the diagram the figure 3.5, there are some kind of example given here. Do not confuse with the numbers. By looking at the numbers, you will feel that it's quite confusing, but actually it's too simple. Okay then, so what we are going to do is, let's see from top to bottom, from left to right. From top left corner, and then go to the next one, and then the next row, and then the next row. Let's look into that in this way. Okay. As per John von Neumann, your program and data are stored in the memory. Fine. So can you see in the top left figure, there is memory and then the CPU registers. So memory, the address is 300, 301, 302, and these are all the instruction memory. So here in this example, the address starts from 3 something, that's instruction memory. The address starts from 9, data memory. Let's assume in this way, in this example, okay? So there are 3 instructions in memory at location 300, 301, 302. There are 3 instructions. And the data is in, so there are 2 data in 940, 941. Okay. So this is basically the Janua-Neumann concept. The content of the memory is having addressable locations and the program and data are stored in the memory. Can you get the idea? Okay, fine. And the CPU registers, in the previous slides, we saw few registers. PC, IR, AC. PC contains the address of the instruction to be executed next. IR holds the instruction, the fetched instruction. AC for temporary storage. Okay, fine. So now let's see the first, the square box. It's called step 1 in this figure. So let's look into step 1. Memory contains some instructions and some data. And the CPU registers contain some data, like PC contains 300. What does it mean? I'm going to fetch the instruction from the location 300 and I'm going to put it in IR. I did. Can you see that? What is in location 300? 1940. So you fetch it and move it to IR. Can you see IR contains 1940? Okay, fine. Now go to step 2. Then the next, in the first row, second column. That is the step 2. Okay, in all the rows and columns in step 1, 2, 3, 4, 5, memory on your left and then the CPU registers on your right. Okay then. So the memory has 2. Instruction memory, data memory. And here the 3 registers, the CPU registers. Okay, fine. Okay, in step 2, can you see here PC is incremented to 301? This is what we saw in the fetch cycle. After the instruction is fetched and it's moved to IR, CPU automatically increments the PC. It was 300, now it is 301. So CPU automatically increments. So step 2, you know the PC. Okay, why it is 301, you now know already. Now, let's see the IR. What it contains? 1940. I told you in the previous, 1940. Just keep it in mind. 19401. The first digit is 1. Keep it in mind. In the previous slide, I told you the format. Here is the instruction format. I told you the first 4-bit is opcode. And the remaining bits, the 12-bit is address of the operand. Okay, fine. So your instruction is 1940, 1. Put it in a binary. 1 means it is 0001. That is the meaning, is it? 4 bits, first 4 bits, opcode 0001. This one, 0001. If you put it in binary. What does it mean 0001? Load AC from memory. So load AC from memory. Okay then. That means to say, what you see it in memory, put it in AC. That is the meaning. Okay. Load AC from memory. Which memory? Which location? Yeah, you have the address. After 1, in the IR, what do you have? 940. That is the address. Go to the address, take the data, put it into the memory. Put it into the AC. So, go to the memory, 940. Yeah, here it is. What do you have in 940? 0003. Move it to AC. Done. So, this is the first instruction of my program over. That's good. Now, go to step 3. Row 2, in the second row. In the second row, first column. Okay then. So what you need to do is, what your PC says, it contains the address of the instruction to be executed next. So what is the next instruction? It is in 301, which is 5941. So you fetch that instruction, move it to IR. So can you see here an arrow? So you fetch the instruction 5941, move it to IR. Okay, fine. Now I moved it. You need to decode the instruction. Decode means try to understand what is this instruction. I already mentioned that the first 4 digits of the instruction tells you the app code. Here what you have? 5941, 55. Put it in binary. 4 digit, 4 bits. 4 bits, okay. 5 means 0101. Okay, let's go and see. 0101 means what? Can you see here? Add to AC from memory. Add to AC from memory. AC is having 0003. Okay. What I need to add to AC from memory? Which memory location? Yeah, you have the address. 5941. 5 means add. 941 is the address. So go to 941, take the data, add it to AC. Okay. What is in 941? 0002. Okay, so go to 941, take the data, add it to AC. AC already has 3. 941 location has 2. 2 and 3 is 5. Where is the 5? You put it back onto the AC. You see the step 4? Step 4 is done with second instruction. Second instruction is add instruction. Okay then? So, second instruction adds the AC with the memory and the result is again stored in the AC. Done. Did you notice the PC content? It was 301, it's now 302. This is what I told you. After fetching the instruction, CPU automatically increments the PC. So it's now 302. What is the meaning of 302? PC contains the address of the instruction to be executed next. Okay, fine. So what is the next instruction? It's in 302. Go to step 5. Step 5 gives the details. Step 5 contains the instruction to be executed next. So what is that? Go to 302. 302 has 2941. So 2941 is the instruction. Fetch the instruction. Move it to instruction register IR. Okay then. So step 5. Can you see that? Instruction is fetched from the memory. Move it to IR. Okay then. Now look into the step 6. So here what? CPU interprets the instruction and executes the instruction. What is your instruction? 2941. I told you. 2 tells you the app code. 941 is the address of the operand. Okay, fine. 2 is the app code. 2. 0010, that means store AC to memory. Okay. So what does it mean? Store AC to memory. What is the content of AC? 0005. Okay. Store AC to memory. To memory. Which location of memory? Because can you see my memory? It's a big memory. Where I am going to store this 0005. Look at the instruction. Instruction is 2941. 2 is the app code. 941 is the memory location. Address. So, go to the location 941, save the AC content there. Okay then? So, go to the location 941, AC content 0005 is saved in that memory location. Okay then? Moreover, did you notice the PC? PC is now incremented to 303. But anyway, our program contains only 3 instructions. We executed the 3 instructions successfully. Is it fine? So as a just keep it in mind, your memory instructions and data are kept in the memory and the CPU registers are used for the execution of the instructions. Okay, fine. PC program counter contains the address of the instruction to be executed next. IR contains the instruction, the fetched instruction, which is being executed currently. And then the AC is for temporary storage. Okay then. So first CPU fetches the instruction from the memory based on the PC's address. PC contains the address. Okay, based on the address, it fetch the instruction from the memory, and that instruction is moved to the instruction register. After fetching the instruction, CPU increments the PC. It increments the PC. Okay, fine. And then CPU tries to interpret. Interpret means decode the instruction. Okay, try to understand what is the instruction, and then executes the instruction. So this is the idea of instruction execution.